So I'll start today with, as I said yesterday, we will change the context we are working with. And today we will be working, in next lecture, we will be working with germs of biholomorphisms in situ. So we have f from C to 0, which is a biholomorphism. And tangent to the identity. Okay, so this means that it begins with the identity plus higher order terms. Okay, and we are interested in studying, describing the orbits of F. And more precisely, we'll be working with the existence of invariant domains. Okay, so let me just remember, before going to dimension 2, what happens with this problem in dimension 1. I think Jasmin in her talk will also talk a little bit about this in dimension 1. So we have f of z, which is c plus higher order terms, not the identity. Okay, so here we have a whole understanding of the behavior of the orbits. They are described by the so-called Lopez-Hernanz flower theorem. Okay, so this tells us that there exist two domains with 0 in the boundary. Which are alternatively invariant and attracted by the origin by F or its inverse. And together they cover a whole neighborhood of a whole puncture neighborhood of the origin. And moreover, we find the so-called Fatou coordinates, which are in this domains, which are called petals. We find conjugations with the unit translation. Moreover, in each domain, omega, there exists an injective, holomorphic injective map such that phi f equals phi plus 1. Oh, phi minus 1. C equals C plus 1. Okay, this is Lopez-Hernanz flower theorem. So let me just make a picture to understand what the theorem is saying. So we have, for instance, if we have a map where k is equal to 3, plus a c4 plus higher order terms, we can always make a change of coordinates so that this is minus 1. Okay, so we have 3 invariant petals for f, which are bisected. We have 3 attracting directions, which are the positive real axis, and it's the third roots of the positive real axis. Okay, and here we have some petals which are invariant for f, and the orbits converge to the origin tangentially to these directions. Okay, and we can do the same thing for the inverse, and we have the repelling petals. We have that this direction is attracting for the inverse. So for F, we have this repelling petals. Okay, so just to give an idea of the proof, okay, well, the first, I will work only with K equal idea of the proof. I will assume that K equals 1, okay, so otherwise it's just a ramification, K equals 1, okay. So the behavior, well, it's reasonable, the behavior we find, because in this case we find we have f of c, which is c minus c squared plus higher order terms. This is very close to the flow of the vector field minus c squared. This is very close to the time flow of the vector field minus c squared partial with respect to c. So the orbits behave like this. Sorry. And here we find the attracting petal. Okay. So the idea of the proof is just to make to translate my dynamics to infinity with a new coordinate w. W equals 1 over z. Okay. And in these coordinates, we can write f. Here. You can write f this, in the coordinate w as the translation plus something small, plus 1 over w. Okay, so in this new coordinate, it's very easy to find the existence of these invariant domains. Okay, this is small if w is big enough, so if we are away from the origin, in a sector, in a domain like that, okay, the iterations of my map will be very close to the identity, to the unit translation, sorry. So we'll be in a cone like this. Okay. So this is invariant. Okay. I will not go into the details of the construction of fat coordinates. Okay, so this is the description of the dynamics in dimension 1. We have the behavior in a whole neighborhood of the origin. So what happens now in dimension 2, or higher dimension? In higher dimension, dimension 2. Okay, so in this case, we are very far from having a complete behavior description of the dynamics in a whole neighborhood of the origin. So, the problem I'll be dealing with is the existence of these petals in dimension 2. Okay, so we have two possibilities for we are in dimension 2. So we can look for petals of dimension 1 or petals of dimension 2. Okay, I will address mainly the existence of petals of dimension 1 and maybe talk a little bit about petals of dimension 2. Okay, so we will say petals of the analog of petals. We can have dimension 1 or dimension 2. These will be called parabolic curves. And these will be called parabolic domains. Okay. So they are domains, connecting domains. Of dimension either 1 or 2, such that they are invariant, that have the origin in the boundary, and which are invariant under the action of gamma of f and attracted by the origin. Okay, so what I'm going to explain today are the, let's say, the first two results concerning the existence of these domains in dimension 2, mainly the existence of parabolic curves. Okay, so I will talk about Ecalle and Hakim's theorem, which guarantees in arbitrary dimension the existence of parabolic curves when we have some condition on F, and then Abate's result, which tells us in the case of C2 that we can always find a parabolic curve. Okay, so let me just give some definitions. And I will relate them to the results we showed yesterday for vector fields. So assume we have F. We can write it as sum of homogeneous polynomials, x plus pk plus 1 of xy plus higher order terms, y plus qk plus 1 of xy plus higher order terms, where these are homogeneous polynomials. And this is non-zero. Okay. Well, let me just say, before stating the first result, let me just mention that, of course, if we had an invariant curve for F, an invariant curve, an analytic invariant curve, then the restriction to this invariant curve would be a one-dimensional tangent to the identity map. So we would find immediately the existence of parabolic curves, but usually this is not the case. So if F had an analytic invariant curve, the restriction would be, we could apply Lofa-two-Flower theorem, the existence of parabolic curves. Would follow from Lofa-two-Flower. But this is not the case in general. Okay, so if we write our map in this way, we will define the so-called characteristic directions. A characteristic direction for F is a direction V such that pk of V, qk of V equals lambda V for some complex number lambda. Okay, as you see, this is very similar to what we defined yesterday as what you know as the tangent cone of the vector field. Okay, so now we will, in a few minutes, we will make the connection between these two concepts, and we will say that the characteristic direction is non-degenerate if lambda is not 0. Okay, so the result, the first result concerning the existence of parabolic curves was proved by Ecalle in the context of resurgent functions, and later by Hakim with more standard methods. Okay, so it tells us that if we have a non-degenerate characteristic direction, we always find parabolic curves. If F has a non-degenerate characteristic direction, V, then F, there exist parabolic curves for F, where the orbits converge tangentially to B. Okay, and this also holds in higher dimension. The definition is exactly the same for characteristic direction, for non-degenerate characteristic direction, and the result is also true in higher dimension. Okay, so I forgot to say where is the interest of these characteristic directions. They satisfy the following property. If we have an orbit that converges to the origin with a tangent, this tangent direction has to be a characteristic direction. Okay, so they are the only possible directions of tangency of an orbit. If an orbit n of p of f converges to 0 tangentially to a direction, V, then V is a characteristic direction. Okay, so this result tells us that with this non-degenerate assumption, this lambda is different from 0. This characteristic direction, these non-degenerate characteristic directions, always support a parabolic curve. Okay, so now I'm going to make the connection with the results we saw yesterday, and to do so, I will see how we can associate to F to any tangent to the identity biholomorphism a formal vector field, and which are the properties that are preserved by this relation. So we have a tangent to the identity biholomorphism in C2, in Cn it's the same thing. So we can always associate to it a formal vector field. There exists a unique formal vector field X, whose time one flow is F. Okay, we can define the time one flow as for analytic vector fields. So we have that F of xy is written as this expression xn acting as a derivation. We can understand a formal vector field as a formal derivation. So the vector field acting as a derivation here, xn over y over m. Okay, so there is a unique vector field which is singular at the origin with order at least 2, whose time one flow is F. Okay. Yesterday I only talked about analytic vector fields, but all the results I presented also hold, except of course of the analyticity of the invariant curves. All of the results, Seidenberg's resolution of singularity, Camacho-Sad about the existence of a final point with certain properties, they also hold in this formal context. Okay, so what's the relation between how the properties we have seen for X and for F are related? Okay, so some properties of this relation are the following. Well, first, the set of fixed points of F is exactly the singular set of the vector field. Okay, so it is analytic, although the vector field in general is formal. This set, which is the fixed point of this analytic diffeomorphism, is analytic. Okay. It also holds that the first terms, the k+1 jet of f is preserved by in f and in x. Okay, so we can write f as x plus pk+1 of xy plus higher order terms, y plus qk+1 of xy plus higher order terms, if and only if x has this form, k+1 x of y plus higher order terms plus k plus higher order terms partial with respect to y. Okay, so exactly this definition we had for characteristic directions is exactly the same one we saw yesterday for the tangent cone. So in particular, we have that V is a characteristic direction of V of f if and only if it is a line of the tangent cone of x. It is a zero, sorry, of the tangent cone we defined yesterday, Px, which is x qk+1 of xy minus y qk+1 of xy, which gives us the points that are, in the non-critical case, which gives us the points that are strictly singular after blow-up. And another property which is important is that formal curves, invariant curves are preserved. So yes, I'm sorry. This one, I think. Okay, and we also have this property that if we have gamma, a formal curve or analytic, then gamma is invariant for f if and only if it is invariant for x. Okay, the definition of invariant curves, even though it's formal for f, is the natural one as if it was analytic. So we say that gamma is invariant for f if we have that g equals with gamma is in gamma, or if we have a parametrization we have gamma of t, it's a parametrization. Then f of gamma of t equals gamma is a reparametrization of gamma. For some, which can be analytic, which is analytic in the analytic case, or only formal if we are considering a formal invariant curve. Okay, so these are some properties that are preserved by this correspondence between diffeomorphisms and formal vector fields. And well, let's just remark that in general, as I underlined, the vector field is formal. Okay, so usually, in general, it is not convergent. For instance, in dimension 1, if you have a polynomial map or an entire map, the vector field is always divergent. Sorry? Ah, yes, I wrote Q twice, thanks. Minus YP, yes, thanks. Okay, so yes. Sorry, I also wrote it wrong. It's pk plus 1, of course, thanks. Sorry, I called it yesterday because it was a bit strange to say. Usually for maps, you write k plus 1 because it gives you k petals. So usually I keep this pk plus 1 for maps, but I wrote yesterday as pk and qk. It's like that, thanks, sorry. Okay, so what does having a non-degenerate characteristic direction means? We saw that characteristic directions are exactly the points of the tangent cone of this formal vector field. A non-degenerate, okay, we can just do the computation. If B is a non-degenerate characteristic direction, there is another property I should have mentioned, sorry. That we are going to use is that if we consider the blow-up centered at the origin, we can lift this the diffeomorphism F. Okay, there exists. We have here my origin, my map F. We can lift it to these strictly singular points or to these characteristic directions, and we obtain here something, the lifted map, germ of tangent to the identity. It is also tangent to the identity, diffeomorphism. If we are considering these strictly singular points. Okay, so this correspondence with this vector field commutes with blow-ups. Okay, so if we have here the corresponding vector field, formal vector field, and we consider the blow-up, we lift it to a point which is also a point of the tangent cone. Then the associated vector field will be this one. So we have here this commutative diagram. Okay. So this gives us, well, I will see for the last result I will present today. This will give us some final models for F. Okay, it's an analytic diffeomorphism because we obtain it blowing up an analytic diffeomorphism, but we can compute the final forms after resolution doing simply the time one flow of this formal vector field. Okay, so what is a non-degenerate characteristic direction in this context? It's a non-degenerate characteristic direction. It's not exactly, it doesn't have exactly an equivalence with the definitions we saw yesterday. Okay, so we can assume, for instance, that V is 1, 0. So being non-degenerate means simply that pk plus 1 of 1, 0 is different from 0, and qk plus 1 of 1, 0 is equal to 0. So if we blow up and we consider the germ at the point corresponding to this characteristic direction, okay, we obtain for the map F, the lifted and the corresponding point can be written as x plus this is some a different from 0 plus a x to the a plus 1 plus higher order terms and y plus x to the k something. Let's call it lambda, as we did yesterday. Lambda plus mu y plus higher order terms. Okay, and for the map, for the vector field centered at P, we have that this is x to the k times x lambda plus higher order terms plus mu y plus higher order terms. Okay, with lambda different from 0. So it's an element with a blow up, we obtain an elementary singularity, one of the eigenvalues is non-zero, and we don't necessarily have this condition of about the quotient of the eigenvalues not being a natural or the inverse of a natural. We only guarantee that we have an elementary singularity and that this eigenvalue, that the direction transverse to the exceptional divisor corresponds to a non-zero eigenvalue. Okay, so we have this particular kind of elementary singularity. So what we saw yesterday in Briot-Bouquet theorem that holds also one part of it when we have a quotient which is a natural number is that in this case when mu over lambda is not in N, we always find a formal invariant curve which is transverse to the exceptional divisor. It will be analytic if the vector field were analytic, but this is not the case in general. And if the quotient of the eigenvalues is a natural number, is a natural number k, we saw that we have two possibilities. Either we are after resolution in the critical case and we find invariant curves, or if we do not find an invariant curve, we always find some generalized, some invariant transeries. Okay, with logs. There exists always a formal generalized curve. Exists something of this form, aij, x to the I, x to the k log of x to the j, which is invariant. And again, it would be analytic if the vector field were analytic. Okay, so this result about from Ecalle and Hakim can be understood as sectorial realizations of these formal invariant objects. In fact, this is exactly the argument of Ecalle. I will not go into the details of Ecalle's proof. I will just give a quick idea of what he does. And I will explain a little bit the proof of Hakim. Okay, but they are exactly realizations of these formal invariant objects that can be blown down since they are transverse to the exceptional divisor. Okay, we make a blow up. We find here this formal invariant curve or formal invariant generalized curve. And we can associate here, we find these analytic realizations in sectors that can be blown down to this invariant, to these parabolic curves for the original map. Okay, so let me give a quick idea of Ecalle's proof, and then with a little bit more detail, because it will appear in what I will explain tomorrow, what is Hakim's proof. Sorry? Which Hakim? Monique Hakim. Wait. Okay, so very few words about Ecalle's proof. Okay, so it's in the more general context. He works in his theory of resurgent functions, and what he does is to find a parameterization, not exactly something as I'm writing in this case, but a parameterization of the formal curve. We look for, we have a parameterization, and we look for, we consider f of gamma 1 of t, gamma 2 of t equals gamma 1 of t plus 1, gamma 2 of t plus 1. Okay, so you conjugate it with in this way with a unit translation. Okay, we have here this formal solution, and using the Borel-Laplace transform that I quickly mentioned yesterday, you have to change the parameterization because this transformation behaves well with difference equation, not with that general invariance equation. Okay, so he proves that you can perform this process called summability. More general, that he proves that they are resurgent. And you obtain some sectors of some analytic realizations of them. Analytic sectorial realizations. Okay, of this invariant object. So you have to work here in both coordinates with logarithms. And what is Hakim's idea? The more standard proof. So since we have this formal object, x gamma hat of x, a formal invariant, I will call it curve, remembering that it can have logarithms. So we are going to look for a parabolic curve also as a graph of a function. Graph of a function. Okay, the idea is that since we are in an elementary singularity after blow up, we have coordinates where we can work. Okay, so in these coordinates, we have them there, the map, okay, after one blow up. After one blow up. And we can write, I will keep the same name for the coordinates and for f, we can write f as x plus lambda. With a change of coordinates, I will write a -1 as before because I will use Lofa-to-Flower theorem, plus higher order terms, and y plus alpha x to the ky plus higher order terms. Okay. So we are going to find these parabolic curves as graphs of a function u defined in this space. will be holomorphic in a sector bisected by the positive real axis. Okay, because the idea is here. Assume here we can have terms in x and y. Okay, but if y is small compared to x, this will behave as in with the one-dimensional case, and we will find these attracting directions, which in this case are the k roots of the positive real axis, and we find these kind of sectors for the variable x. Okay, so we work with functions which are holomorphic here and are bounded by some power. I will not give the details, but they are bounded by some power of x. Okay, so we look for a function in this space H. So if we can guarantee that it is invariant, if x u of x is invariant, which means writing the invariance equation, this means that f2 of x u of x equals u of f1 of x u of x. Okay, then immediately it will be a parabolic curve, because in the graph of this function, u is small compared to x, so x behaves as in the one-dimensional case we saw before, so the orbits will converge to the origin, and since u is bounded by a power of x, this will also converge to the origin. Okay, so invariance guarantees in this space of functions, it guarantees this convergence to the origin. We obtain a parabolic curve. Okay, and the idea to find a parabolic curve, which is in the more standard method, she obtains the parabolic curves as fixed points of an appropriate map. And the map, let me just give a quick idea of the construction of the map that we will generalize in next lecture. So the idea of the fixed point u is constructed as a fixed point of a map T from the space H, which is mainly based on this construction. T of u of x is essentially, you want something here, u of xn minus f2 of xn u of xn, where xn is f1 of xn minus 1 u of xn minus 1, the orbit of the first component of the orbit of these points. Okay, so if you have something, a fixed point here, it's easy to see that this gives you a function that satisfies this invariance equation, but this is too big to make a map from H to H. Okay, so you simply modify it with some term that has to do with the dynamics of the orbits of this map. Okay, these orbits. This is the map F is very close to the orbits of this equation. Alpha y. So y is x to the minus alpha. Okay. So with this factor alpha, this here you put x to the alpha minus.
Sorry, when you say the xn. I mean xn. When you define it xn,
Yes?
the one started at x.
I don't understand the question, sorry.
X0 is x.
X0 is x, yes, yes, sorry, yes. X0, yeah, X0 is x. I mean, yes. Yes. Yes, yes, of course. Yes. Here it should be x0, okay. So you modify this this initial construction that doesn't work because it's not it does not stay inside H to okay, and here you have to put some x0 to the minus. Okay. So you show that this is a contraction in this space. And you find the parabolic curve. Parabolic curves, in fact, K parabolic curves. Okay, so in this, I wrote that sector bisected by the positive real axis, but we can do the same thing in the K attracting directions of this map x minus x to the K plus 1. So we find the parabolic curves. We find parabolic curves. Okay, so that's the idea of her proof. So about parabolic domains, let me just give a quick idea of the result. As I said, this works also in higher dimension. The proof is essentially the same. We find, for non-degenerate characteristic directions, we find these parabolic curves. And what about parabolic domains? So theorem by Hakim. Tells us that if we have a non-degenerate characteristic direction, and after blow up, this alpha has a negative real part, and the real part of alpha, alpha being that the quotient of this quotient of the eigenvalues after blow up, and the real part of alpha is negative. Okay, so here we have this node behavior. Here the orbits, if the real part of x is negative, so this will all converge to the origin. So we can enlarge the parabolic curve to a parabolic domain. We find parabolic domains. We find a parabolic domain. Well, again, K parabolic domains. Omega, where the orbits converge tangentially to B. And moreover, we also find Fatou coordinates. In this case, we conjugate to the map, which is the unit translation in the first coordinate and the identity in the second one. So they are foliated by parabolic curves, these parabolic domains. Moreover, we find there exists this phi from omega to Z2, holomorphic injective, such that phi f phi minus 1 of ZW equals C plus 1 W. So we have this generalization of the construction of Fatou coordinates, and we have that these parabolic domains are foliated by parabolic curves. Okay, and this is also holds in a higher dimension. Okay, here, the dimension of this parabolic domain will depend on the number of eigenvalues which have negative real part. Okay, so what happens if we do not have a non-degenerate characteristic direction? So in Z2, we can always have a parabolic curve or a curve of fixed points. Okay, this is Abate's result. And it only holds in dimension 2. Okay, so in this sense, we can understand this theorem by Ecalle and Hakim as an analog, as a discrete analog of Briot-Bouquet theorem. It's a little bit more general because we allow these generalized invariant curves. Like a kind of analog of Briot-Bouquet. Okay. And we have also a discrete analog of Camacho-Sad theorem. Okay, so we have theorem by Abate, which tells us that if we have a tangent to the identity diffeomorphism in C20 always has either a curve of fixed points or a parabolic curves. Okay, so this is an analog of Camacho-Sad theorem. Okay, so the proof by Abate is just to adapt this construction of this proof of Camacho-Sad theorem to this context of diffeomorphisms, introducing an index showing how it behaves under blowups and performing this argument of showing the existence of a point satisfying the good properties after the resolution. Okay, but with this approach of the infinitesimal formal vector field, we can give a quicker proof, which is simply you have your map F. Okay, you have the corresponding vector field X. You know that there is by Camacho-Sad theorem, we know that we find the resolution, we find a point where this is a strong direction. Okay. This is a strong direction. A non-zero eigenvalue. And a singularity, which is elementary, and this direction corresponds to a non-zero eigenvalue. Okay. You do the same thing for this, for the map. Okay, so you find here this point, and here you are exactly in the conditions of Hakim's result. So here you are exactly in this situation that you obtain after blowing once a non-degenerate characteristic direction. So, because here you find this using this commutativity property I mentioned. So here we are in Ecalle Hakim situation. Okay, so you find here the parabolic curves, and you can blow them down. So you find here the parabolic curves that they are not necessarily, you find here parabolic curves in Ecalle Hakim's result. The fact of having a non-degenerate characteristic direction, well, this guarantees that here you don't have a line of fixed points. Here you could have a line of fixed points. So, okay, you have not necessarily a parabolic curve, but a curve of fixed points. Okay, this direction could be, since you are performing several blow-ups, this could be, if you are not in this case, is because this is a line of, here you have a singular, a line which is singular for the vector field or fixed points, or a fixed point, a curve of fixed points. Okay, so you have, or you work, maybe it's easier if you work from the origin with an isolated singularity. Okay, so you are not in this case, and you find these parabolic curves that blow down to a parabolic curve for the origin and map. Okay, and in the last 2 minutes, let me just announce what I will be talking about in the next section, in next lecture. So, so what I'm going to explain on Thursday is 2 generalizations of Ecalle and Hakim's theorem. Okay, so we can understand Ecalle and Hakim's theorem we can understand it if we are considering the situation after blow up. This tells us that these invariant curves that correspond to a non-zero eigenvalue, these strong invariant curves, okay, as I said, it's more general, also with generalized invariant curves, but we can see it as a proof of the fact that these strong formal invariant curves are have realizations as parabolic curves. Strong invariant curves support parabolic curves. Keep that in arbitrary dimensions. So it is true that every invariant curve, not only every formal invariant curve, not only the strong ones, support parabolic curves. So we will see that this is the case. Is this true? Also for weak invariant curves. And so we will see that this is the case, and also as in their theorem, in arbitrary dimension. And also it shows that non-degenerate characteristic directions support parabolic curves. So is this true in general for characteristic direction, not necessarily the non-degenerate, which are, is it true for degenerate characteristic directions? And we will see that it is also true, but this case only at so far in dimension 2. Yes, in dimension 2. Okay, so these are the results I will talk about in the next lecture. Okay, so thank you very much.